Alright, so in this video we're going to look at CC11, which is extraction of metals, and this topic begins with the reactivity series. And the reactivity series is just this big long list of metals that goes from the most reactive at the top to the least reactive at the bottom. You don't need to know this off by heart, but you do need to know how to use it to be able to predict how metals are extracted. Now, what I mean by extracted is that metals, if you just leave something like potassium out in the environment, it's going to react with water, it's going to react with oxygen, and it's going to form something different. It's going to form potassium oxide or potassium hydroxide. Similarly, if you've got iron and you just leave it outside, it reacts with the oxygen, it reacts with the water, and it forms iron oxide, which looks like rust. And all of the metals are going to do this. You're not going to find pure calcium outside, you're going to find calcium oxide after it has reacted. And often a lot of these oxides are just these powders, and they're not very useful. So what we need to do is take these powders and turn them back into pure metals that we can use for different things. So aluminium, for example, we use to make airplanes, but aluminium oxide would not be able to be used to make airplanes. So we're going to be trying to extract our metals, so which is taking a compound, the metal has reacted, and then getting the pure metal back. And we use the reactivity series to look at the method that we're going to use. Now, I've highlighted carbon and hydrogen here because these guys are non-metals, and we use them to see what method of extraction we use. So everything above carbon, these guys are all going to be extracted using electrolysis. So for example, if I had sodium and it reacted with chlorine and I had sodium chlorine, I would have to use electricity to split sodium chloride up to get sodium and to get chlorine back. So I'd use electrolysis, I would split it up, and I would get sodium and I would get chlorine. Anything that's less reactive than carbon, so these guys down here, you can use what's called reduction with carbon. And we're going to look at that in more detail in a second. Reduction with carbon. Sorry, I can use that for copper as well. And anything at the very bottom of the reactivity series, silver and gold, these guys are so unreactive that you can find them pure. You can find pure gold, you can find pure silver. You don't need to be able to extract the metal, it's already pure. But everything else, you need to be able to extract the metal first. Right, I just want you to do question 1 on your sheet, just A, B and C. So press pause, use your reactivity series and have a go. Actually, I'll move that. Now press pause and have a go at question A, B and C. There's lots of right answers here for the top one, as long as you've gone for something above carbon. So aluminium, magnesium, calcium, lithium, sodium, potassium, they're all acceptable. Extracted using carbon, you can say zinc, iron and copper. I've gone for iron. And does not need to be extracted, I've gone for silver. You could also say gold. Right, the next thing we need to look at is what do I mean by reduction with carbon. So what I'm going to do is I'm going to take zinc after it has reacted with oxygen, and it will be zinc oxide. And what I do is I take my zinc oxide and I react it with carbon. Now, because carbon is more reactive than zinc, we get a displacement reaction where carbon takes zinc's place. That means carbon will now be bonded to oxygen, and typically when carbon and oxygen are bonded together, we form carbon dioxide, and that means zinc is not bonded to oxygen anymore and is just by itself. It's called just zinc by itself. If I do that with iron, I'm going to get the same thing. I've got iron oxide. I react it with carbon. Carbon is more reactive than iron, so carbon is able to take iron's place. And when it does, again, I get carbon dioxide and the iron is left by itself. Now this is called reduction with carbon, and you need to know your definitions for oxidation and reduction in terms of oxygen. So oxidation is anything that gains oxygen, and reduction is when something loses oxygen. Now we do have other definitions for oxidation and reduction. Maybe you remember oil rig, but in this topic, this is what we're talking about. If it's oxidized, it gains oxygen. If it's reduced, it loses oxygen. And you need to be able to identify what's being oxidized and what's being reduced. Now when you're doing this, I'll give you an equation and they'll say what's oxidized and what's reduced. Ignore the product side. You are always picking an answer from the reactant side. If you want something that's oxidized, you want something that's gaining oxygen as you go from the left hand side to the right hand side. And you can see that carbon has no oxygen on the left but has oxygen on the right. Carbon gains oxygen, that means carbon is oxidized. If you're looking for something that loses oxygen, zinc oxide has oxygen, but when it gets to the right hand side, there's no oxygen there. So I can say zinc oxide has lost oxygen, zinc oxide is reduced. Okay, so just make sure you're always picking an answer from this side. Carbon is oxidized, zinc oxide is reduced. Down here, carbon is oxidized, iron oxide is reduced. It's always carbon that gets oxidized. The other thing it reacts with, that is what is getting reduced. Right, I want you to have a go at questions 2 and 3 on your sheet. Alright, so oxidation is gain of oxygen, reduction, loss of oxygen. If I finish off this equation, carbon takes iron's place, forms carbon dioxide, iron is left by itself. You can write carbon dioxide plus iron or iron plus carbon dioxide. When I'm picking what's oxidized and reduced, I'm always picking from the left-hand side. Carbon, we can see, gains oxygen. It goes from carbon to carbon dioxide. I therefore say it's oxidized. If carbon's oxidized, then whatever it reacts with must be reduced. In this case, that is iron oxide. Alright, now I said this method of reduction only works with the elements less reactive than carbon. So what happens if we try it with something more reactive than carbon? So let's just take aluminium. So I've got aluminium oxide and I've got carbon. Now for this to work, the carbon and the aluminium need to swap places, but they will only swap places if carbon is more reactive than aluminium. And we can see from our reactivity series that aluminium is more reactive than carbon. That means they will not swap places and you get no reaction. So if carbon is more reactive than the metal, so zinc, iron, copper, it can take the metal's place, it can bond to oxygen and you form the pure metal. But if carbon is less reactive than the metal, and it is for all of these metals, this reaction won't work and we have to use electrolysis instead. Now I'm going to answer this question with you because the way we phrase this is quite specific. Explain why aluminium cannot be extracted from aluminium oxide using carbon. First thing we're going to state is aluminium is less reactive than carbon. No, it's not. Aluminium is more reactive than carbon. Aluminium is more reactive than carbon. So what does this mean? This means that carbon cannot take aluminium's place. Okay, it cannot take its place because aluminium is more reactive. Now, the next question asks you how you could get aluminium from aluminium oxide. If this won't work, well, what can you do? We've set up here, you would have to use electrolysis. So you would need to use electricity to split up aluminium from aluminium oxide. And it asks you in the question to state how it's extracted. All right, so that's just going to be electrolysis. But to identify a problem with this method of extraction, and your problem is that electrolysis is very expensive. It requires a lot of energy to split aluminium and oxygen apart, and that means the method is going to be quite expensive. Alright, there is another method that you can use, and this is called phytoextraction. And in phytoextraction, you plant lots of trees on soil that you know contains some metals. So for example, this soil could have lots of metal ions in the soil. So maybe copper ions are in the soil. And you plant loads of trees on soil where you know there's metal ions. And what will happen is that the plants will take the metal or ions into their roots, and you end up with lots of copper ions. It's usually copper. You'll end up with lots of copper ions all in the roots of the plant. Now notice that I'm saying copper ions. Copper ions are aqueous. They're dissolved in water, and that allows the plant to absorb them. If it was big chunks of metal, the plant wouldn't be able to take the metal into the roots. But the metals are ions, they're dissolved in water, and they can be absorbed. And the plants absorb all the metals into the roots, and then what you do is you pull up the plants, including the roots, you burn the plants, and then from the ashes you get pieces of metal. So this is another way of extracting metals from the ground, okay, and it's called phytoextraction, and it uses plants. Now the next question you're asked to describe the process. All right, so we'll do that together. Describe the process of phytoextraction, and we're just going to write plants absorb metal ions from the soil through their roots. Okay, the plants are then burned and the metal is extracted. Now, what's an advantage and a disadvantage of this method? One disadvantage of this method, it's slow. Okay, you have to plant trees, you have to wait for them to grow. It is quite slow. But an advantage of this method is your other option of getting copper from the ground is mining. You have to dig big mines, which isn't very good for the landscape because you're digging big holes. It's also not very safe, and it's also quite expensive. So give one advantage of phytoextraction, it reduces the need for mining because it gives you an alternative to mining. Okay, and mining, can you just write, is loud and it's unsafe. All right, so why do we want to reduce the need? It's loud and it's unsafe. And there's another method here called bioleaching. All right, in bioleaching, what you do is you have a bacteria. So you've got lots of in here you would have lots of bacteria, and the bacteria can break down the metals into solution. And again, this typically works with copper. We use bacteria to break down kind of metal solutions into ions. So describe the process of bioleaching. We don't need to be able to explain it in detail. We'll just say bacteria used to form solutions containing metal ions. So your key word here is bacteria. You're using bacteria. A disadvantage, you get toxic waste products with this. Toxic waste products. But an advantage, you can say exactly the same one as above. It reduces the need for mining, and mining is bad because it's loud, creates noise pollution, and it's unsafe. So this method, you're using bacteria, you breaks down the kind of metal ores into solution, and then you can take out the metal ions. Now below as well, you've got advantages and disadvantages of recycling metals. So rather than trying to find new metals from the ground, can we recycle our old methods? Again, your advantage of recycling is it's going to reduce the need for mining. All of this reduces the need for mining, but a disadvantage of recycling, recycling is not cheap. It's not cheap because recycling has to be collected, it then has to be sorted, and then it has to be processed, like turned into something else. So it's quite a long process, and it involves a lot of people, which means it's not actually cheap, but it does reduce the need for mining. Last thing here, LCA. LCA is called a life cycle assessment. And essentially, it's what you need to consider if you're trying to manufacture a new product. So just say you're in industry and you want to make this new product, you need to be able to do up a life cycle assessment. And in your life cycle assessment, you need to say, what are the raw materials? What are you going to be using to make your new product? Maybe it's a new piece of technology, but what are you going to use to make your new piece of technology? You're also going to need to say how the technology will be disposed of when it's done. So what are you going to use to make it? How will it be disposed of when it's done? Because you need to be able to consider the environmental impact that these new products may have. Right, that's a quick whistle stop tour through extraction of metals, but make sure you are doing the exam questions on them as well, to just see how well you understand this stuff.